Section 6.1 is composite functions, and so it shouldn't be surprising at this point that we're starting a new chapter, getting into chapter 6, and we are talking about functions. Like I mentioned way back in the beginning of the semester, this whole first 3 chapters we're going to be working on is about functions, and so we introduced the basic idea of the function in chapter 3. In chapter 5 we looked at polynomial functions and rational functions, and then in chapter 6 we're going to continue exploring some different types of functions. We're going to look at what's called a composite function in section 6.1, and then that's going to set us up to where we can continue into chapter 6 and talk about exponential functions and logarithmic functions. And so kind of hitting some other concepts along the way, but like I said, section 6.1 is composite functions. We're going to look at a few different things here with regard to composite functions. Form a composite function, so we'll see what is a composite function. Then of course we're going to talk about the domain of the composite function and a little calculus application of finding the components of a composite function. So first, let's just define what a composite function is. There's kind of an application or an example of a situation here. It says, suppose that an oil tanker is leaking and you want to determine the area of the circular oil patch around the ship. So you can imagine the situation here. You're out in the ocean and there is an oil tanker that's leaking. As you can tell, I am an artist, and it's leaking oil. And it's more or less a circular oil patch that's leaking out of this tanker. And it's probably killing all the fishes, and there's a lot of people that are pretty upset about it. But that's the situation. We have a tanker in the water, and obviously this is an overhead view of the tanker in the water, but in case your imagination is failing you, this is water, this is oil, and this is a tanker. And there's your art lesson for the day. Alright, but oil's leaking, okay, and suppose it says that we want to determine the area of the circular oil patch around the ship. So you can imagine this right here is roughly a circle, and so we want to know what's the area of that circular patch of oil. Okay, and so we know that since it's leaking, obviously the patch of oil is going to be getting larger and larger as time goes by. It says oil's leaking from the tanker in such a way that the radius of the circular patch of oil is increasing at a rate of 3 feet per minute. So the size of that patch of oil really depends on how long it's been leaking, right? And so we could set up a little formula for the radius of that circular patch of oil and say that R of t, that's the radius after a certain amount of time, is 3t, that's 3 feet per minute. So for instance, after 20 minutes, the radius of the oil patch, R of 20, is, multiply that by 3, you get 60 feet. So, if we want to talk about the area of the circular patch of oil, we're going to talk about, well, how long has it been leaking, right? The longer it's leaked, the bigger that patch of oil. Okay, I hope you're with me so far. Now, if we want to talk about the area of that patch of oil, that's a circle, right? This right here is a circle, and it has some radius r. Okay, and again, that's increasing as time goes by. The area of a circle we know is pi r squared, right? So after 20 minutes, we said after 20 minutes the area is going to be a of 60. Now that's 60. Remember, after 20 minutes the radius was 60 feet. So that's pi times 60 squared, or 3600, and there should actually be a little pi square feet right there. So after 20 minutes, 3,600 pi square feet is the size of that oil patch. Now we could also kind of put these two together, because again the area depends on how long that thing's been leaking, right? So what we can do, that 60 that we plugged in right here, A of 60, remember that was R of 20, right? That's what we got up here. 60 is R of 20. So A of 60 is also the same as A of R of 20. Okay, so the argument, the thing we're plugging into that function A, is actually another function. That 60 was R of 20. And so you notice this little statement where you have a function inside of a function. This is what we would call a composite function. Okay, A of R of 20. That composite function is taking two functions and putting them together. And then you can talk about the area of that oil patch after a certain amount of time. A of R of 20. Take the 20, that's the time, plug it into the R function to get how many feet the radius is, and then from there that goes into the area function to calculate the area of that patch of oil. Okay, composite function. That's what we're dealing with. One function inside of another function. And so that's what this right here says. This A of R of t is that composite function. It's anytime you've got a function inside of another function, and this is the kind of the general definition. But if we've got two functions, f and g, we can evaluate g of x, plug the x into some x value into g, and then we can evaluate f at g of x and get f of g of x. That's again just plugging in g of x into the f function. And the notation for this, it looks like this. That little circle, it's not a times, okay, that's a little tiny circle, and f of g of x. Okay, that's the same as plugging the g of x function into the f function. And we'll talk about the domain here in just a minute, but that's our notation that we use. Okay, and you can almost think of this composite function as an operation. It really is what it is. It's taking and doing something with two functions, kind of like back in chapter 3 when we added two functions together. We multiplied two functions together, you know, f plus g or f times g of x. Well, here's another operation. We can do a composition, f of g of x. So it's sort of the same idea as those operations we had in chapter 3. I think that was section 3 point something. I don't remember what section it was. It was in chapter 3. Okay, so let's get used to this notation and figure out what's going on here. F of g of 1, it says, suppose that we have this for f of x and g of x. It's right here, so two functions, f and g. F of g of 1, just using our definition of the composite function, looks like this. The first thing we need to do is ask ourselves, okay, what is g of 1? Okay, g of x is 4x, so that's 4 times 1, which is 4. Okay, so this is f of 4. And now we can go up here to our g function and say that's 2 times 4 squared minus 3. And if you work that out, I believe that's 29. So f of g of 1 is 29. Part B here, we're switching it around. Now we're doing g of f of 1. Now these are not the same. Okay, not the same. When you switch the order around, that's not necessarily going to be the same answer. Okay, let's see what we get. This is now g of f of 1. So it's switched around. So the first thing we need to figure out is, what's this f of 1? That's 2 times 1 squared minus 3. And 2 minus 3 is negative 1. Okay. Now g of negative 1, that's 4 times negative 1. That came from this g of x function, which is negative 4. So g of f of 1 is negative 4. Again, these two answers we got not the same, right? So when you switch that order around, f of g is not the same as g of f. Not always, anyways. Now sometimes it is, and we'll see here in a little bit what that means if f and g of f are the same. But for now, just know that they're usually not the same. Okay, C and D. Here we've got f of f. So we're using the same function twice. So this is the same as saying f of negative 2. So the first thing we need to do is find out what's f of negative 2. Again, that was 2x squared minus 3. I believe that's 5. So now we plug that back into the f function again. 2 times 5 squared minus 3 should be 47. Okay. So we're just plugging that x value into that function twice. Okay. First it goes to the inside function, and then the result goes into the outside function. We get our answer. Same thing with g of g. So this is g of negative 1. So the first thing we need to do is figure out what's g of negative 1. Remember, g of x here is just 4x, right? So this is 4 times negative 1, which is negative 1. And then 4 times negative 1, whoops, actually, negative, how about negative 4? That would probably be a better answer there. And then that makes this negative 4 here. And that's going to be negative 16. Okay. So that is that. And there's kind of a concept here. If you have like, and this is a classic picture you'll see a lot of times. Say you've got like f of x and you've got g of x. Whoops, that's not what I wanted. And you're wanting to do f of g of x, so you want to put those together. When you do that composition, your x value, first it goes to the inside function. Okay, so first it's going to go into whatever g of x is. Okay, and then it's going to come out of there. This is now g of x. Again, you can always think of a function in terms of like input and output. So we input an x and we got a g of x from that output. And then that goes into f of x. And then the result is f of g of x. So if you'll kind of remember that picture, when you're doing f of g of x, it always goes to that inside function first. So you evaluate x into the g of x, whatever that inside function is. The result of that goes into the outside function, and then that's where you get the f of g of x from. So that's a pretty useful thing. Really, you're just kind of chaining two functions together, thinking about input and output. Remember, this is your input, and then this is your output. But then that quickly becomes your input to your x, your f of x. Then here's your output. Okay.